let's look at the harmonic series and talk about why it is divergent. We can start by just listing it out. We'll start with n equals 1. So we have 1 divided by 1, which is 1. And then 1 divided by 2, 1 divided by 3. And n is just going to continue to increase. 1 divided by 6, 1 divided by 7. Let's do a couple more. And this is just going to continue forever. What we want to do next is prove that this is actually a divergent series. What we can do is we're going to replace each term with a number that is less than or equal to it. More specifically, we want to use the largest power of 1/2 that is less than or equal to each term. Up first, we're just going to copy 1. And looking at 1/2, we want the smallest power of 1/2 that is, again, less than or equal to it. Since it is a power of 1/2, we'll just copy it. And then for 1/3, we want to replace it again with the highest power of 1/2 that is less than or equal to 1/3. So we want to go smaller. What's smaller than 1/3 and a power of 1/2? 1/4. So we can replace 1/3 with 1/4. 1/4 is already a power of 1/2, so we'll copy down 1/4. And 1/5. We want to replace it with a number that is a power of 1/2, but also smaller than 1/5. That power is 1/8. So we can replace 1/5 with the smaller fraction 1/8. And we'll do the same thing with 1/6, 1/7, and 1/8. And then the smallest power of 1/2 that is less than 1/9 would then be 1/16. And that's going to continue forever. We'll keep replacing those fractions with smaller numbers that are powers of 1/2. Now let's see what we have. We have 1 plus 1/2. And notice what happens if I add these two. 1/4 plus 1/4 is 2/4, which is 1/2. And then if I add these next 4 fractions, we get 4/8, which is 1/2. And then 1/16, we'll add that 8 times to get 8/16, which is 1/2. And we'll continue this pattern over and over forever. We have 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2, and that's going to continue for a very long time. And so this sum, let's call it S, is just adding 1/2 over and over and over. So we're adding up to infinity. This is diverging. This diverges. And remember, S is actually smaller than the sum that we started with, because we're replacing these fractions with smaller fractions. So if we have a smaller sum that diverges, that means the original sum, the harmonic series, must also diverge. It diverges. Up next, we have just a few notes. If a sequence A sub n is convergent, then any subsequence of A sub n must also converge. So if we have an infinitely long sequence that is convergent, then it makes sense that if we take any smaller part of this long infinite sequence, it must also be convergent. If we want to show that a sequence diverges, then all we have to do is show that any subsequence of that sequence diverges. So if we have a very long sequence and we just chop it up into a smaller part, and that smaller part diverges, then the whole thing, the entire sequence, must be divergent. Next, we have a theorem. If the series a sub n is convergent, then the limit of the sequence must be 0. So let's think about that. Think about what we did with sequences. If the limit of a sequence equals a number, then it converges. If it doesn't equal a number, it diverges. Well, now we're talking about series, so we're adding those numbers. So if the limit of that sequence ends in, say, 5, and you're just adding 5 plus 5 plus 5 plus 5 over and over and over, it's going to diverge. So what's the only number that we can add at the end of that sequence over and over and over in order for it to diverge? It would have to be 0. So we're eventually adding 0 plus 0 plus 0 plus 0 on the end of that sequence to add up to our series, meaning we have a convergent series. Now we do have to be careful because the converse of this theorem is not true in general. It's not a biconditional statement. If we have a convergent series, then we know that the limit of the sequence is 0. But we can't read this backwards. Just because we have a limit of a sequence equaling 0, that does not indicate automatically that the series is convergent. An example of that would be the harmonic series. The limit is indeed 0. The limit of the sequence is 0. Right? If we looked at 1 over n, the limit of that would go to 0. But if we're adding them all up, then it's going to actually diverge. So we just have to be careful. We can't read this backwards. The limit of the sequence equaling 0 does not necessarily mean convergence. It's easy to forget that. Again, think harmonic series. That will prove it to us. So to show a series diverges, we can show that the limit as n approaches infinity of a sub n is not 0, or potentially does not exist. So if the limit of the sequence is not 0, or if it doesn't exist, then the series of a sub n must be divergent. It diverges. This is called the test for divergence. We'll see an example of this in a few minutes. Here are a few properties that we can use to help us determine what a series converges to when it is convergent. If we have a constant, we can just pull it outside of the sum, evaluate the sum, and then multiply by that constant. If we have the sum of two different sequences, we can split that up into two sums and evaluate those separately. Remember, if one of these sums or series is divergent, then the overall series will also be divergent, and we can also do that with subtraction. In this example, we want to determine whether the series is convergent or divergent. And if it is convergent, we can then find its sum. Notice that we have common factors of 3 in the denominator. Let's see what happens if we factor out a 3 in the denominator. So we have 1/3 times, you can think of that as 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, and so on. Recognize that these fractions are what we saw with the harmonic series. So we have 1/3 times the sum from n equals 1 to infinity of 1 divided by n. that harmonic series we proved earlier diverges. So if we have a constant times a divergent series, this is just a constant multiple of a divergent series, the harmonic series specifically, which means this must diverge. In our next example, it looks like we have factors of 2 in the top and factors of 5 in the denominator. Let's pull out 2/5. Let's factor it out and see if that helps us rewrite this or recognize any kind of patterns. So we have 1 plus 2 over 5 plus 4 over 25 plus 8 over 125 plus 16 divided by 625. That pattern is going to continue. Let's see if we can rewrite this now. We can think of this as 2 to the 0 divided by 5 to the 0 plus 2 to the first divided by 5 to the first. Looks like that'll be 2 squared and 5 squared. 2 cubed, 5 cubed, 2 to the fourth divided by 5 to the fourth, and that continues. So it looks like we have a geometric series. We have the sum, n equals 1 to infinity. 2/5 is our a value. Looks like 2/5 is also the r value. So we have a geometric series. A is 2/5 and R is also 2/5. To figure out what this converges to, since it's geometric, we can do A divided by 1 minus R. That is 2/5 divided by 1 minus 2/5. 2/5 divided by 3/5. And simplifying that, we get 2/3. So this sums to 2/3. In the next example, it looks like we don't have a geometric series. We don't have any common factors in the top or bottom that we can factor out. So one thing we can do is do the test for divergence. As you learn more and more tests, you'll get better at determining which tests to start with. Right now, we really only have a few, and the test for divergence is one of the good ones that we can start with if you think it may diverge. We're going to take the limit as n approaches infinity of the sequence 2 plus n divided by 1 minus 2n. And remember, to attack that, we divide the top and the bottom by the highest power of n that occurs in the denominator. So we now have limit as n approaches infinity. In the numerator, we get 2 over n plus 1. In the denominator, we get 1 divided by n minus 2. And now evaluating the limit, this first fraction goes to 0, so we get 1 in the numerator. In the denominator, this fraction goes to 0, so we have 1 divided by negative 2, which is negative 1/2. And note that that is not 0. So since we get a number that is not 0, we took the limit of the sequence and we got a number that is not 0. That means that the original series diverges. And as a reminder, if it's equal to 0, that does not necessarily mean we have convergence. Think harmonic series. But if it's not equal to 0, we can say the series definitely diverges. In our last example, let's see if we can start by rewriting this using some exponent rules. We have the sum. We have 3 to the n plus 1. We can think of that as 3 to the n times 3 to the first, using those exponent rules to break that up a little bit. And then we have 4 to the negative n. Let's push that to the denominator to force that power to be positive. From here you may see it. We can pull the 3 out front, just 3 to the first. We have the sum, n equals 1 to infinity. And we have 3 to the n divided by 4 to the n. We can think of that as 3/4 raised to the n. At this point, you may recognize that this is a geometric series, but I like to fix that exponent, just personal preference. I like the power to be n minus 1. So in order for that to happen, we need to pull one fraction out of that. Pull out 3/4. That'll be our a value. And now we have 3/4 to the n minus 1. And from here, we can see that it is indeed geometric. We have a geometric series. A is 3/4. R is also 3/4. So we have 3 out front still, times, remember we do 3 times a divided by 1 minus r. So a is 3/4. 1 minus r is also 3/4. That's 3 times 3/4 divided by 1/4. That is 3 times 3, which is 9. So here the series converges to 9.